Hello everyone. So this is DP Shahi and we are going to study few of the concepts from Mathematics 101. In short form it's Maths 101. So the objective of this whole session will be basically focusing on these three major topics. First we are going to see numbers. What are numbers and what are the basic classification of numbers are there, and then we are going to learn a very important topic. Now why I am saying so? Because this topic, so called the method of contradiction, is the part of discrete mathematics, and discrete mathematics usually in India are taught in graduation and post-graduation levels, and that to be in quite detail. So method of contradiction we are going to see, and by this method only we are going to prove few of the irrationalities of the numbers. Like I have taken the 4 examples which we are going to see in this particular session, how we are going to prove square root of 11, 5 minus square root of 3 plus 2 square root of 5, and 1 divided by square root of 2. See, sometimes I'm going to say just root, that will be must be considered as square root unless and until I mention cube roots or any other roots. So if I'm just saying root of 2, that means I'm saying square root of 2. So let's begin our session with the very brief introduction about numbers. See, numbers usually we mean, or by whenever we say what are numbers are basically mathematical objects which are used to measure something, to count something, and to label something. All right. So as far as this classification of the number is concerned, we have been taught since from nursery itself, in the nursery or from the beginning of the kindergarten or the education. When we begin our education, numbers are taught, and those numbers are usually considered to be the natural numbers, the counting numbers. In our kindergartens or the nursery classes, we start with counting numbers 1 to 10. So counting numbers are there. First classification will be considered to be the natural numbers, which are also known as the counting numbers. And after that, we keep on learning the things. The age passes by, we grow up, and we come to know that numbers are not just the counting numbers. There are many different classifications also. And we have studied that, and we are studying. In fact, this number topic, which we will be dealing in this particular session, will be regarding real numbers. And these numbers are actually being the part of the first chapter of class 10th. See, in 9th also we have done numbers. In 8th also we have done. And in 7th, 6th, 5th, and since the beginning we have been learning the numbers. So the first one I have discussed about the natural one, the counting numbers. Then we next classification can be like whole numbers. They can be even numbers, odd numbers, rational numbers, irrational numbers. All right, and there are others numbers too. The integers are there. Okay, that decimal numbers are there. So there are quite classifications, or that I am trying to say. And we have been studying since the education career, since the dawn of the education of ourselves. So as far as the major classification of the number is concerned, we put numbers into 2 major categories, which will include each and every numbers which are existing on this planet. Or we have discovered. So the first classification, the major classification that we put, is the real number, and another one is the complex number. So these 2 classification they can accumulate all the other classifications. All right. So these two classification are basically the major sets or the major accumulation of the other numbers. Okay. So let's start with the real numbers, because in class 10th the first chapter is named as real numbers in mathematics according to the CBSE or the NCRE. So what are real numbers, by the way? Well, real numbers are all the numbers. Okay, all the numbers except the complex numbers. So basically think about any of the number till if you are in 10th, or if you are in 10th, that means whatever the number that you are coming up in your mind, it is definitely going to be, the major probability is going to be the real numbers. Say it's negative numbers, positive numbers, decimal numbers, real numbers, rational, irrational, all sort of numbers are classified over there. Now what is the definition of the real numbers? The real numbers are all the numbers except the complex numbers. So to understand it, if I'm going to start defining real numbers, so it is going to be very much lengthy, very much it will be constituting lots of subcategories and sub-classifications in it. So what we can do is we can simply make a good definition by like this: all the numbers except the complex numbers. So now this definition is going to be like not too much fancy one, but still it works. So to understand it, we can say all the numbers except complex numbers are the real numbers, and to further know more about, we should know the complex number. If we know complex number, we can exclude the complex number from all the classification of the numbers, so we will get what left with will be the real numbers. So I'm going to define both of them. Well, the first one I have defined it. After that, I'm going to discuss about the complex numbers too. But before we enter in the complex numbers, let's see what are the major subcategories of the real numbers which we are concerned right now in this lecture. Well, real numbers are further can be classified. Again, it's a broader classification. Real numbers can be classified as far as the broader sense is concerned: rational and irrational numbers. Now I'm going to discuss about the rational and irrational in the next slide, but before that, just have a small glimpse of the complex numbers. Well, complex numbers are a bit fancy. Now why I'm saying this fancy? Because these numbers are literally introduced in India as far as the CBSE board is concerned in class 11th. Alright, there is a name of this chapter called complex numbers itself. I don't know, it may be a 5th chapter or the 4th chapter, we have to check it out. Now what is the complex number? The question is, see, the complex number is basically a number, okay, which have a very fancy, okay, which has a very fancy part associated with these numbers. These are the numbers which have iota. See, this is I, this iota. All right. Now iota is the Greek letter. It is just a symbol. It looks like I, the small letter I. This I has a value. This iota has a value. It is equivalent to square root of -1. All right. So that's iota, which makes any number complex number. Because in mathematics, if you look into the history of the mathematics and the numbers, this iota is something which have literally annoyed great mathematicians as far as the history of numbers are concerned. And in fact, till today, we have been unable to solve and get the exact value of square root of -1. We don't have any value, so that's why we simply take a square root of -1 and we denote this as iota. We consider it as a constant value which doesn't have which doesn't have we can call it already defined, well-defined number in mathematics. Yeah, you can say like it's iota square is 1, sir. -1 rather. Iota square is negative. See, there are a lot of operations that we can operate on iota. But as far as iota itself is concerned and the definition and the value, the exact value of the iota is concerned, well, it is not as far as explored till today. But this sign of iota, which is equivalent to square root of -1, is actually something which have annoyed mathematics, mathematical thinkers and mathematician a lot, literally, trust me. Well, as far as the numbers representation is concerned, it is denoted by usually C, capital C or small c, nobody cares, with two real parts. See, these A and B are the real part of the whole complex number. These are the real parts. So A can be, say, -5, 2, 3, -5, 2, 3, 7, 8, square root of 1, whatever. Square root of 1 is 1 actually. Square root of 3, consider it. Or B, in the same manner B. So A and B are the real parts, and this thing is something which make the whole system, the whole number as a complex number. So what we have seen with this discussion, that complex number are numbers only with a special with a special factor associated with the numbers. So can we say complex numbers are the real numbers with special factors? We can't. But to as far as the broader understanding is concerned, we can say that it is it's a set of a number which have an additional part associated with it, and that additional part, if it is there in the system, if it is there, that additional part makes this complex number. The whole system makes to be considered as the complex number. And what's that additional part? The iota part. What is the iota? It is just a Greek letter which represents something. And what it represents? It represents square root of -1, which have till now no defined value. That's the complex number. However, you people are going to learn many operations, how to perform certain kind of mathematical things on like the arithmetics parts, and other parts also in class 11. There is a whole chapter based on complex number in class 11th. So that is the very brief introduction about complex numbers. So back to the real numbers. So now we can define like real numbers are all those numbers excluding the complex numbers. So what we say we have a numbers, all the existing numbers in this universe. Should we call it universe? Because maybe aliens. Okay, just consider it. All the numbers that has been discovered, invented by humans. If we are going to put in a bag, and we are going to take all the complex number out of the bag is left with other numbers except the complex number, and that bag will be classified as real numbers. So that is a very brief introduction, a brief explanation, or rather I should call it, about the real numbers and the complex numbers, people. Okay, so let's move on the discussion further. So we are going to study a real number in this whole the lecture part, the session part, and a real number, that to be the focus is going to be on these two further classification, the rational numbers and the irrational. Now I'm going to discuss what are rationals and irrational numbers. So let's see. So as far as the rational numbers is concerned, see, we have done this in 9th grade also. All right. So also in, if I'm not wrong, in 8th grade also we have done this. So let's see what are rational numbers. As far as the definition is concerned, on the three major portion we define rational numbers. Okay. The first one is all the numbers which can be denoted by in the form of P over Q. All right, where the things should be, remember, is these P and Q will be co-prime and Q cannot be equals to 0. Now, what will happen if Q will become 0? See, any number divided by 0 in mathematics, it comes not defined. All right, there is a term for such scenarios. So anything divided by any number divided by 0 is not defined. All right, there is a well explanation for that also. If I'm going to include that, I think the whole objective, just remember it, that any number divided by 0 we get is not defined. That means whatever the solution that we are going to get in the mathematics, it is not going to be well defined. Say if a bunch of people are doing with a set of numbers, and they are ultimately dividing it and they are getting a particular number. Another set of numbers people are doing and divided it by 0, they are not going. I mean, the expectations of the answers in different scenarios and checkup field will not going to matter. Will not going to matter as far as their similarities in the answers are concerned. It is not defined. It is not at all defined. If you divide any numbers with 0, it is going to be not defined in mathematics. As far as the coprime is concerned, I have wrote it over here that P and Q will be coprime. That means P and Q will have only one, number 1. All right, 0, 1, 2, that 1 as a common factor. Say for instance, I have taken an example over 2 over 3. That means 2 have a prime factor of 2 and 1, and 3 has a prime factor of 1 and 3. So 2 has a common factor with 3 will be 1 only. So 1 is the if there is a if we do the prime factorization of the two numbers, the numerator part and the denominator part, as far as the P and Q are concerned, if we are getting only 1 as a common factor between both of them, then it is considered to be the coprime numbers. All right. So these are the examples of your rational numbers. The first one I have explained it. Say negative 5 over 7. That has also 1 negative. That has also 1 as a prime factor. As far as the 0 is concerned, because 0 by 1 is itself a rational number. 9 is also a rational number. 9 by 1. So anything which do not have anything on the denominator, we consider it to be the 1. That has been taught in 7th, 6th, 5th. So in the earlier classes you have already been taught with this concept. So let's see what are as far as the decimal description. As far as the decimal description is concerned for the rational numbers, we can consider both kind. Say terminating one, a number after a particular decimal, it terminates. Say, see 3.25. So the number ends over here. So it's a terminating decimal. So terminating decimal is also rational number. All right. And non-terminating but repeating. That means that, say for instance, 2.375, 375, 375, and it will keep going. All right. So these kind of numbers are also considered to be the rational numbers. Now, what is bar over here? It is another representation to write, non-repeating but non-terminating but repeating kind of a rational numbers, decimal numbers, or rational numbers of decimal kind. This means that negative 3.5787, 5787, 5787. I'll keep saying this. 5787. And it will never end. It will go. So instead of writing 4 or 5 times, we simply write one time and put a bar over it, just like this that we have done. So what we have learned in rational numbers, basically with 3 major categories, we can define rational numbers. As far as the P over Q is concerned, it can be represented. As far as the decimal numbers are concerned, we can write rational numbers in 2 descriptive forms. One, if the decimal numbers are terminating, we consider as rational numbers, the examples I have discussed. As far as the non-terminating but repeating is concerned, that means the numbers are not terminating, they are not ending, but they are repeating too. So these are the 3 explanation or the classification how we can classify rational number further. So as far as definition or the classification of the rational number is concerned, this is what we have to understand. All right, people. So let's move on to the irrational part. See, in a very straightforward answer, we can say that all the real numbers. Why I'm not considering numbers? Because if I'm saying it numbers, that means I will be including the complex numbers too. So I'm excluding that part. That means I'm including only the real numbers. So we can call it like this: all the real numbers except rational numbers. What we get is irrational numbers. So it's another way of defining it. But further, if we going to define, so you people can also think about rational numbers like that only. All the real numbers which are not irrational are rational. See, what the problem is, it is very straightforward and it is very less informative. If I'm going to write like these, it is not going to be too much fruitful for you people to understand. So okay, let's see what irrational numbers actually are. So as far as the P and Q form is concerned, irrational number cannot be written as P by Q form. Alright, P divided by Q, we can't write we can't represent irrational numbers like P over Q, P by Q. So it cannot be represented as P by Q. As far as the decimal, what are the examples? Say square root of 11. All right, we can't say square root of negative 11. If I'm going to say like square root of negative 11, it will become a complex number, because square root with negative sign makes iota, and that iota is actually the part which makes any number a complex number. So square root of 11 is irrational number, and all other three parts too. Well, we are going to prove all these four parts of the numbers. All these four parts of the numbers, we are going to prove it, in the session only. As far as the decimal description is concerned, they are non-terminating. That means they are not going to end, but also they are not going to repeat too. The numbers are going to be different. All right. See, if we see here, it's 2.01 001 0001 4 times 01 and we are doing it. That means the repetition is not there. See, 110s are adding up over here. Not like adding. They are we are including. We should rather call it including. As far as this number is concerned, 3.141592 and so on. See, this is actually I have taken from the value of pi, from the value of pi. So it is also non-terminating, it is not terminating, and it is not repeating too. So hence it is considered to be the irrational number. All right. So we are going to do things further. Okay. Hello. So as we have seen till now, we have seen irrational numbers and a few of the examples, and we have discussed a few of the associated properties with them. Now let's move on to the next section and see what we have. So as discussed, after discussing numbers, we are going to discuss method of contradiction. Now this is one of the most important part of mathematics, and why I'm saying this, because this method of contradiction is one of the major part in discrete mathematics. This section of mathematics is usually introduced in college levels, basically graduation and post-graduation. I have mentioned this earlier too. So let's see what this method of contradiction actually have with us. What sort of things are there in this particular method. So this method of contradiction has basically four major parts. All right. So first of all, by this, by the way, we prove any very obvious statements. All right, we prove mathematically obvious statements, which in you know in day-to-day life, things are already considered as universal truth. But in mathematics, we need to somehow, somewhere, we need to prove that too. The universal truth must be proved in some scenarios, in some situations in mathematics. So this type of method actually works a lot in that kind of questions. So I'll give you an example, like mathematically prove why sun rises in east, not in west, not in north, not in south. Why from east only? So mathematically we can prove that too, you know, and in that scenario this method is going to work a lot. In the same manner, to elaborate on this particular method, I am going to take a very funny example, so that with fun and with enjoyment you will be able to understand this particular method of contradiction, which is a part of discrete mathematics. However, this is in your syllabus, not like with some taglines or with in depth, but they have used your NCRTs by CBSE uses this method, but not in a well classified and in-depth manner. But I'm just trying to put some of the light on this particular topic so that you will understand how things works. So method, as far as the method of contradiction is concerned, it has basically 4 major parts. All right, the first part is like we have to assume a particular statement to be false, which is actually true. You know, just like that sun rises in east. That statement is a universal truth. That is a true statement. However, when I'm going to prove that actually sun rises from east, I am going by this method, I am going to consider the assumption part here. The first part, I'm going to assume that sun does not rises from east. Alright, so I'm going to take the opposite statement, what I needed to be proved. Alright, after that, I'll try to prove my own statement, which I have taken, the false statement. I'll begin to prove, and I'll begin to give the arguments in support of the assumption that I have taken, which is actually false, by the way. So after trying to prove that statement or the false statement, trying to prove that false statement and the arguments and the the supporting things that I'm going to provide, I'll keep on doing that, and ultimately I will come to a contradiction that whatever I have taken, whatever I have considering is not going to happen. It is impossible to happen. Hence our statement, the fourth part now, hence our statement that we have taken as a false one, alright, is actually false. Hence the true statements become true. Alright, so it seems a bit confusing, but actually it is not. It is very simple. Let me provide you that funny example in order to explain this method of contradiction. See people, this thing is not something which you don't need in your life. You actually need this a lot. As far as your graduation is concerned, any field, if it has mathematics, you are going to come across with this particular method. So if you have the glimpse of this method right now, it is going to help you a lot in the your education career. So let's see that funny example, what I'm going to consider it. So let's consider, alright, let's consider in a class of 40 students, a boy named Pushkaranand. Okay, and he's a boy, obviously. Now prove that he is indeed a boy by the method of contradiction. So it's a bit a funny one, but actually it makes sense as far as the method of contradiction is concerned. Let's try to explain this illustrative example and try to understand this particular method. Alright people, so let's begin. So here I am going to in this particular video I'm going to explain how this this happens, this proof can be done. So the objective of the illustrative example is to prove that, one second please, boy. So according to the the step that are associated with with the proof of contradiction, we are going to see how this works. So first step was to assume that Pushkaranand is actually, so we are here assuming that let us assume that Pushkaranand is not a boy. This is the statement that we have assumed, because the first part of the contradiction method was to assume, and right now we are going to exclude the factor of transgender. So we are including only two factors here, the male one and the female one. That means the boy and the girl. We are excluding the transgender one. All right. So that means either Pushkaranand is going to be girl or either Pushkaranand is going to be boy. However, he is a boy, so I am just going to prove it that indeed he is a boy. So to start with, so let's so what we have done here, we have taken the assumption part that let us assume that the Pushkaranand is not a boy, excluding the factor of the transgender. That means Pushkaranand is going to be a girl. We have assumed the opposite one. He is a boy. We have assumed that he is a girl. I mean, how can we say he and girl too? I'm just saying it. Just forget the English part, the literature part. Just try to concentrate on the maths part. So we have assumed that Pushkaranand is not a boy. He is a girl. All right. So now the proving part. Okay. If he is a girl, that means the subject Pushkaranand is going to have some of the features associated with the girls. That's the proving part. The first part is the assumption one. Now the second part is the proving part, the supportive arguments that I'm going to provide in order to support the assumption. So I have begun with like some of the features that the subject Pushkaranand must have is number one. I have taken enlarged breast. So we are considering Pushkaranand, the subject, must have enlarged breast. All right. And the second part, after careful analysis, we are going to say the subject must also have another property. Say Pushkaranand must have a vagina, which is known as a reproductive organ, that must be present in him. So in the subject. So after that, say another feature that subject must possess, say some of the supporting hormones, estrogen and progesterones, that must be there. Also the subject must have ovaries, a pair of ovaries, because these are the basic four. There are a lot many characteristics too, but these are the basic four characteristics that a girl must possess in order to be called as a girl. All right. So we have considered the first part. We have considered the assumption part, that we have considered that Pushkaranand is a girl. Now, if the subject is girl, then the supportive argument should be true. We have wrote it like these four things must be there. But you know what? After now the contradiction part. After careful analysis, we come to know that all these four statements that we have taken, enlarged breast, female reproductive organ, that is vagina should be there, the hormones part and the ovaries part, all these four statements which we have taken, that must be there, but actually it is not. After the careful analysis, we come to know that these supportive arguments for a girl is absent in Pushkaranand. Hence, now comes the contradiction part. Hence, the assumption part that we have taken that Pushkaranand is a girl contradicts now. Therefore, after coming to the contradiction, that our assumption that we have taken that the subject Pushkaranand is going to be a girl is actually not true. So what was the assumption? That assumption. So that we have assumed that let us assume that Pushkaranand is not a boy contradicts over here. So our assumption now here becomes incorrect. Alright, which means it is false to say that Pushkaranand is not a boy, is a girl. It is going to be false. Therefore, what we are left with now? We are left that if Pushkaranand, the subject, is not a girl, that means the subject is going to be a boy. So see, this type of proof we can do, and we can say that the assumption cannot be true. It is impossible to say that Pushkaranand is a girl. Hence, Pushkaranand must and indeed a boy. So you people have now seen how this method of contradiction, works. All right. So, so that was the basic funda to understand how, how this the whole method of contradiction works. Let's start. Okay, so to prove square root of 11, sometime I'll be calling root of 11, excuse me. To prove square root of 11 is irrational number, alright, which is a fact, by the way. Right now we are going to prove it, alright, and that to be by the method of contradiction. Alright, so a few of the things which are associated with this are the very important one, the very first one, which is known as to be the assumption part. The assumption part that we have to take. Alright, so let's see what we have. So assumption part. So what we are going to assume? Obviously, we are going to assume, or we are going to let it, that square root of 11 is not an irrational number. So whatever we need to prove by the method of contradiction, we let that statement to be false one and we take the opposite of it. Only we consider the two scenarios, either this or that. Out of these two, only one thing is going to be true. So we are going to assume in the assumption part that root 11 or the square root of 11 is not an irrational number. So what we are going to consider, either the numbers are going to be rational or irrational. Hence we have considered this is not an irrational number. That means it is a rational number. That's what we have assumed in the assumption part. So as you guys know that if it is not an irrational, hence it will be rational. Therefore this root 11, square root of 11 can be written as P by Q form. That is a general formation form of the rational number, where P and Q, as you people quite aware, and I have discussed it earlier also in the section of rational numbers, that P and Q are going to be co-prime numbers. Now what are co-prime numbers? The co-prime numbers are those numbers which have only one as a common factor between them. That means P will have say n number of factors. Alright, Q will have say n number of factors. However, P and Q will have only one as a common factor. If this scenario happens, that means P and Q are co-prime to each other. Alright, and one more thing that this should always be in mind, that Q cannot be equals to 0. Alright, so Q cannot be equals to 0. Now what will happen if Q is going to be 0? Alright, if Q is going to be 0, then the number that we have let, that is the square root of 11, will become not defined. If Q, and it's a fact that in denominator if it is 0, then the number will become not defined. It is a well proven fact already. We are going to consider it like that only. So let's proceed. The assumption part we have seen, all right, that the first section of the method of contradiction, which is known as to be the assumption part, that we have seen. Now what we are going to do is we are going to stick with our assumption and try to give some of the arguments associated with it in order to support our assumption, and ultimately a kind of a contradiction is going to come, and that will contradict our assumption, and ultimately we will prove it. All right. So by proceeding portion, or the process of proving portion, let's see. As we have taken here that square root of 11 can be written as p by q. We have seen over here too. So by simply shifting this q over there, it will be in the multiplication part, and let's square on both the side in order to kill this square root. All right. So by squaring on both the side, we will get 11 times q square equivalent to p square. Now this statement we have to stick with it. Now one thing, before we will move on, and we are going to see further proof of it, we have to stick with one thing, that according to your NCRE book, okay, there is a very beautiful theorem given in it. That theorem is named as Theorem 1.3 in the book of yours only. It states that a particular number is the factor of another number's square, then that number is going to be the factor of the previous number's square that we have taken. That means if a number is a factor of a particular number square, then this number is going to be the factor of that number's square's square root 2. I mean, say if there is a number, say w, okay, if this w is the factor of a square, then this w is going to be the factor of a also. So if a number is the factor of a particular number square, then it is going to be, this number is going to be the factor of that number also, whose square factor it was. Okay, so let's prove this statement only, and then we will move on. Then we will be back on our proof. See, this proof is not, as far as the examination is concerned, this proof is not going to come in your exam to prove it. But however, our motto is to know more and more about less and less. So we are going to see this proof also. However, this proof is not going to come in exam, like I just said. So let's see. Let's say there is a number a, all right, and if there is a, then its square will be a square, obviously. Say if a numbers prime factorization will be, say just for instance, p1, p2, p3, all right, and a square will be p1, p2, p3 times p1, p2, p3, and so on, you know, as I am showing over here. So by multiplication these two stuff, we will get p square, p1 square plus p1 square, p2 square, p3 square, and so on, you know. So I guess there is no doubt in this particular statement. So I have taken a number and its square, and I have another in the next step I have taken a's the numbers prime factorization, say p1, p2, p3, and similarly if we can see the square of the numbers prime factorization will be same. So I can write like this also. So according to theorem, as we know, according to theorem, if a number, say w, is the factor of the prime factor of, say, a square, then we can say like this, that a square will be equivalent to this prime factor w times something. It is a very basic fundamental you can call it property, that if there is a number, say a square, whose factor is w, so a square can be written as like this, w times some number, You know, any number can be represented like this. Any composite number you can write like this. Okay, so it can be written as like this. All right, so I think there is no doubt in this particular statement. Moving on, as we are also pretty much aware, and we have shown over here that say a square will be like this one. This is the value of a square, so I can write it like this also. Now I'm going to equate these two equations, because a square is this much and again a square will be this one. Now this a square is from here, okay, and this one we have taken as a basic mathematical property. You know, any composite number can be written as the prime factorization of any stuff, any number you can call it. So by equating these two, so this times this equivalent to w times this particular one. See, I'm just taking it open, you know, empty braces. It can be anything in it, you know. So we can say that this will be this w will be able to divide this one, because this w must be either p1, p2 or p3 and so on. This w is the part of, I'm just writing it over here only to make it more understandable. So this w will be the part of either p1, p2, p3, or you can call it, it will itself be p1, p2 or p3. So if we are considering w as a prime factor, see, we have mentioned now over here that w is the prime factor, and these are p1, p2, p3, these all are the prime factors. So it in order to equate these two equations, w must be either p1, p2, p3. That means w will be equivalent to either one of these all prime factors. Okay, so it is a very basic mathematics and very easy to understand this stuff. So it has to be true. If it is not, that means it is not obeying the basic fundamental properties of numbers, which is not possible. You know, they have to. So, well, this particular property is also written in your book under the name of the fundamental theorem of arithmetics. Okay, so if it is one of it, that means it will be, as you can see, if w is going to be one of p1, p2, p3 or any one of it, then w will also divide a also, because a has the value of p1, p2, p3. So in another sense, or in other words, we can say that if there is a number which divides, say the number is w, if a number divides a square, then that number, say w, will divide a also. So this was the theorem, and this was a very short glimpse kind of proof that we have seen over here. So it is a very simple proof, you know, and I have written the fundamental theorem of arithmetic also here for you people, which states that, this is also given in your book only. Okay, so which states that according to the fundamental theorem of arithmetics, it states that every composite number can be expressed as the product of the prime. Okay, as the product of the prime, and this factorization, this prime factorization that we are talking, is unique apart from the order in which the prime factors occur. This, let me read it. Every composite number can be expressed as the product of the primes, and this factorization is unique apart from the order in which the prime factors, apart from the order in which the prime factors occur. All right. Hence, we can see from over here only, and all the discussion, we can name it as 1. Okay, this whole statement we can name it as 1, and from 1 and with the property of mathematics, simple property or the arithmetic property, we can say that if something divides, say w divides a square, a square or the a square's factor, then it will divide a or its factor. In short, you can call it in a very straightforward, you can call it, if w divides a square, then w will divide a also. Okay, so back on the proof of a square root of 11. So where were we? I think we have squared this, and we have wrote 11 times q square equivalents to p square. We have square root, we have squaring after squaring on both the side, and by this theorem 1.3, which we have just proved that. So this we can call it this 11. Okay, on the next sheet I'm going to show it. Do pay attention. Okay, this is one of the important one. So as we have seen, okay, so as we have seen that 11 times q square equals to p square, this 11, so this 11 is going to be the factor of p square also, and this 11 is going to be the factor of p also, according to the theorem that we have just proved, that we have just seen. Okay, moving on. So if 11 is the factor of p, then we can write it like this. P equals to 11 times some number. Okay, any number. Now how come this equation comes over here? See, consider this p as a dividend, this 11 as a divisor, this dp will be the quotient. As 11 was the factor of it, that means the remainder is going to be 0. So we can write any number like this, or you can simply just write it, I think, and simply we can write like this. One second. And simply we can write like this, that p equivalent to 11 times dp. So we are pretty much aware of EDL, Euclid's division lemma. The name maybe you will not be pretty much aware, because I haven't used this name in my whole the curriculum of this video. So what we can write directly, we can write like this: p equals 11 times dp. Okay, because over from here only, because 0 has no value, you can eliminate it directly, and you can write like this: p equals 11 times dp. Okay, now always remember this, and if there is a need, just make some sort of bubble or something like that. So we got the value of p, isn't it? 11 times dp. So what we are going to do is, we are going to take this same equation, okay, and we are going to put the value of p over here, okay, which is equivalent to p equals 11 times dp. That's what we have got it by simple theorem of arithmetics. From theorem of arithmetic, any number can be represented as a factor times anything. Any composite number you can write like this. Okay, moving on. So after putting this value of p in this equation, it will look like this: p square, this p square was 11 times q square. I have written this whole equation, just copy it down here only. Now I'm going to put the value of p over here. So this will become the square of it, and this will, the RHS part is as it is. So this will become 11 square is 121 times dp square equals 11 times q square. So 11 we can cancel out. This 11 will be shifted over here, and it will be cancelled out. This 11 over 11, and we will cancel it out. We will get 11 times dp square equals q square. dp square equals q square. Now we got two similar kind of equations, See, 11 times q square equals p square, this equation. And now we have got quite similar equation like this. 11 times dp square equals to q square. That means here 11 was the factor of p square and p also by the theorem of 1.3. In the same manner, we can say that 11 is the factor of q square as well as q. Okay, by the same theorem, theorem 1.3 from your NCERT itself, which we have proved also. We can write it like this again. 11 is the factor of q square as well as q. So now we are going to get a contradiction. Now what will it be? Have some patience. Let me show you over here. Please pay attention. Now the 11 has become the factor of p and p square. Again 11 has become the factor of q square and q. Okay, now how this is gonna happen? Because we have taken p and q to be the co-prime numbers. We have taken in the assumption, isn't it, that p and q are the co-prime numbers. That means p and q will have only one as a prime factor. But after doing some of the basic mathematics, we come to know that p and q has not only one as a prime factor, it has another factor 11 over here. Hence we hit the contradiction. Let me mark it over here. See, p and q are the co-prime. That's what we have assumed. That's what the assumption was. That means it has only one as a common factor. But after simple mathematics and doing simple mathematics in the subsequent part, we come to know that p has a factor, p and p square, in fact, both things. P square and p has a factor of 11 and q square has a factor of 11 also. That means it is not co-prime. So that is the contradiction. What is the contradiction? That p and q are not co-prime, which we have assumed that that p and q are co-prime. So we hit the contradiction over here. So we met a contradiction. Okay, it can't be possible. We met a contradiction. Hence our assumption that square root of 11 was not an irrational, that means it's rational, has become false or incorrect. Hence square root of 11 is indeed an irrational number. Now let's prove a few of more examples. We are going to take another one. Okay, we are going to take another one. To prove that 5 minus square root of 3 is an irrational number by same method of contradiction. So let's see how we're gonna do this. The assumption part. So we are going to assume that 5 minus square root of 3 is not an irrational. So what will it be? It will be rational. So we are just assuming this, which ultimately we are going to meet with a kind of a contradiction, and our assumption is going to be false, and hence it will become irrational. That's the motive of this proof. So as we have assumed that it's a rational number, therefore this number can be written as p by q form. And again with the same details, p and q are such that p and q are co-prime. That means co-prime means that p and q will have only one as the prime factor, or the common factor between p and q. Okay, it has the common prime factor of 1 only. And another statement we are going to mention over here, that q cannot be equals to I beg your pardon, q cannot be equals to 0. If it is going to be 0, then the number is going to be not defined number. That also we have discussed. So this number can be written as p by q form. where P and Q are co-prime to each other. That means they have the only factor of 1 and Q cannot be equivalents to 0. Moving on. So what we can do is we can simply shift. Can we? Yes, we can. We can shift this 5 over here. This is the rational part. So this 5 is going to be over here, then it will be minus. So P by Q minus 5. See, P by Q is the rational part and this minus 5 is also rational. So rational minus rational always end with rational. So this whole portion will be rational only. Again, moving on, can I shift negative? This negative means negative 1. Negative 1 over here? Yes, I can. So if negative 1 is going to be here, then it will be just like this. So rational, this whole rational with negative sign will be rational only. And I have shown here how this negative sign can be shifted over here. See, this negative can be written as negative 1. So this negative 1 will go over here. All right. So it will be, if this negative 1 will be here, then it will be in divide part. Then if we will reciprocate it, then it will be the same one, because 1 reciprocate with itself will become 1 only. So negative sign is negative itself over here. So it will become this much. So don't, you people should not confuse with that I have shifted this negative 1 over here. It will be into divide. Yes, it will be into divide, but after reciprocating it, you will get this only, because this is multiply. When we shift multiply over here, this RHS part, then it will go into division. However, the reciprocate of the negative 1 will be negative 1 itself. So I'm writing it directly over here. So this is the explanation how this comes. So now, see, negative rational will end up with rational only. Okay, it's a well proven fact. So this whole term is rational. But now here comes the contradiction. Negative rational is rational, which cannot be equals to irrational. See, this yellow portion is rational part. Okay, and one second. See, this whole yellow part is the rational part, but this one is irrational. So our assumption, how come this is going to be possible? Irrational cannot be equals to, rational cannot be equals to irrational, or vice versa. So our assumption is going to be totally incorrect. So whatever we have assumed, that this statement, 5 negative root 3, 5 minus square root of 3 is not an irrational, is incorrect now. And we have met with the contradiction. Okay, it's incorrect and we have met with the contradiction. Hence 5 this was the contradiction. Okay, so hence, see, I'm just explaining it, I'm just telling you that a negative of rational will always end with rational only. It will negative rational is also rational. That's a fact. It's a mathematical fact. Negative rational is rational itself, but rational cannot be equals to irrational. It is impossible. This impossible thing is the contradiction. So I'm mentioning it here with this star. So it can't be possible. Hence 5 minus square root of 3 or 5 negative root 3 is indeed an irrational number. So this is how we can prove the irrationality one. 3 plus 2 square root of 5 is an irrational number. Alright, so how are we gonna prove this? We are going to prove this by the method of the same, by the method of contradiction. Okay, so let's see. So basically, whenever we talk about method of contradiction, we always talk about the 4 major parts which is associated with the method of contradiction. Which are as follows. So the first one is the assumption part. Okay, so we are going to assume whatever is needed to be proved. We are going to assume the opposite of it. So here we need to prove that 3 plus 2 square root of 5 is an irrational number. So what we are going to assume? That 3 plus 2 square root of 5 is not an irrational number. So anything which is not an irrational number, and if it is a real number, then we can say that it's a rational number. Excuse me. So 3 plus 2 square root of 5, we have assumed that it's an irrational number. Okay, so another way of saying that it's an irrational number, we can say it's a rational number, because if something is not irrational number and it is a real number, then we can say it is actually a rational number. So we have considered that 3 plus 2 square root of 5 is not an irrational, or in another sense it's a rational number. So this can be represented as p by q. Okay, 3 plus 2 square root of 5 can be represented as p by q, because we have let it, in the assumption part we have let this is rational, so we can represent like this, where p and q has to, and here p and q must possess the basic characteristic, few of the characteristic associated with it, and they will be that p and q are co-prime. First thing first, they have to be co-prime. That means p and q have only 1 as a common factor. All right, and the second part is that q, or the denominator part, cannot be equivalent to 0. If it is going to be 0, then the whole system that we are taking, the whole the statement that we are taking is going to be not defined. And if a statement is not defined in mathematics, that means we cannot perform any of the relation or the operation of mathematics on a not defined statement. If it is not defined in mathematics, how can you do anything on it? It's impossible to perform any sort of operation. So we have to mention this, that q cannot be equals to 0. Moving on. So what we did here is we have simply shifted this 3 on the RHS side. So this is positive 3. When it is going to be on the RHS side, it will become negative. Now this whole statement will be like this. This is the rational part, and we know that 3 is rational. So 3 by 1 is rational basically. So p by q minus 3, that is a rational one. So rational minus rational is always end up with rational. It's a basic fundamental property of maths, that rational number subtracted by a rational number end up with rational number only. Okay, so this whole statement we can call it that this is going to be rational one. Now this 2 is here. Let me stop it for 1 second. Yeah, this 2 is over here. So it is in multiplication. When we are going to shift 2 on this whole statement, it is going to be in the division form. See, I have write it here. So again we can say that this whole system is the rational one. Divided by rational is always end up with rational. So again this thing is going to be like I have I have shown here, that this whole system divided by 2, which is here only, can be written as rational divided by rational, which is end up with rational only. So this whole statement is rational. However, on the LHS side, it is irrational, because we are very much known. We have to write it here, or we can just call it that square root of 5 is irrational. But this is on LHS side, whereas on the RHS side, this whole system is rational. So how come this is going to be possibility? Irrational cannot be equals to rational. Hence, we met with a contradiction. Now, this statement is very important. So, what we have done till now, we have performed the three basic functionality of the method of contradiction. The first one is the assumption one that we did. Okay, and after that, we have given the arguments to support that, and ultimately we have met with the contradiction. That LHS, on the LHS side we have irrational number, on the RHS side we have a rational number. This cannot be possible, so hence it's a contradiction. This is the third part. The first one is the assumption, the second one is the proceeding part, the process part that we have to give in support of the assumption one, and the third part becomes what is the third part? The contradiction part, that we have met with the contradiction. And the fourth part is that after a contradiction, whatever we have assumed has become incorrect, a false statement. Hence the assumption's opposite part The assumption opposite part. Here, what is the assumption? That it is a rational number. That's the assumption. It's a rational number. So, it has become false. It has become an impossible, an incorrect statement. Hence, our number 3 plus 2 square root of 5 cannot be rational. Hence, it must be, and it indeed is an irrational number. So, you people have seen that how we can simply and with this particular method, how beautifully we can prove that the whole number is irrational number, whatever the number is given in the question. So we have proved over here, isn't it? So that was it. Let's see another example to prove that 1 divided by square root of 2 is an irrational number. Alright, how we are going to prove? We are going to prove by the same method of contradiction. So let's see. So as we have been discussing, the part of the contradiction, that it consists of basically 4 parts. The first one is the assumption one. So what we are going to take in the assumption part, that 1 divided by square root of 2 is not an irrational number. So what it will become? It will become rational. That's the assumption part. We are just assuming it, alright. So in the assumption, let's write it. So let's assume that 1 by square root of 2 is not an irrational. Say it is rational. So that's the assumption part. So we have let it that 1 by square root of 2 is not an irrational. It's a rational number. Okay. Moving on. So if 1 by square root of 2 is rational number, then we can write it 1 by square root of 2 can be written as equivalent to P by Q, where P and Q, as we are pretty much aware that they are the co-prime numbers. That means P and Q have only one as a common factor between them. That means P and Q have only one as a common factor. And another thing that we have to keep in mind is that we have to define that Q cannot be equivalent to 0. Okay, if Q is going to be 0, then the whole system is going to be not defined, and we will be unable to perform any sort of operation, any sort of mathematical operation on it. Hence, the system will crash. The whole statement will become unsolvable and attemptable, you can call it. So one thing here we have to keep in mind, guys, that before performing any sort of mathematical operations and any sort of solutions or solving any statement, we have to always remember, we have to rationalize the roots in the denominator. There is a well-defined reason for it, why we need to rationalize, why we always said, since the irrational numbers are introduced in our life, why we have been always compelled by other teachers or even the books also, that we should always rationalize the denominator. There is an explanation behind that. We just do it, and we hardly even bother to know that why there is a need to rationalize the denominators. Why we need to kill off the square roots or the cube roots or any roots from the denominator. What is the funda behind killing the roots from the denominator? Well, there is an explanation, like I have been saying this repeatedly. There is an explanation for that. Because, my friends, see, if there is a square root or any of the root, cube root or maybe tetric root, pentic root, any root is there in the denominator, it is going to make things more complicated. Now, why I'm saying this, things more complicated? Just imagine you make a computer program, okay? And in that computer program, your software is unable to deal with the irrational number. So what the system is going to consider and what it is going to perform. It is going to convert the square root. Say for instance, I'm just taking a square root in the denominator. The computer system, I'm just giving an example, okay, to make it more understandable. The computer system is going to consider the square root of the number, and it after the consideration, it will convert that into decimal number. Now, as we know that square root of the decimal number lie till the infinity. It is non-terminating and non-repeating kind of the decimal number. And when we are going to convert this into p by q form, which cannot be done, or we are going to kill off the decimal from the denominator part, we are going to keep on multiplying with the zeros like I have shown over here. So this will become huge number, a huge data, okay, which a computer system, I'm giving an example with respect to the computer system. With the computer system, it will overflow. Its register or the memory part or the cache, it's going to overflow. And the system or that software is not going to handle that thing. Okay, so that is the reason why we always need to rationalize the denominator. We always in the very hurry, we should always be in the hurry to kill off the square root from the denominator. If we are not going to do, then the things will become more complicated as far as the softwares and other systems are concerned. In fact, if we ourselves is going to convert this decimal, or if kill off this decimal, then we have to remove the decimal and we have to keep on counting how many numbers are there. However, the numbers will lie till the infinity, hence there will be infinity numbers of 0 behind 1. So it is going to be a very huge and unmanageable number. Hence we need to rationalize. Always we need to rationalize the denominator. Alright, so here I have performed the rationalization. Excuse me. So we have took this one, 1 by the square root of 2, and we are proceeding it. So there is only a single one. Hence we are multiplying it to its numerator and the denominator by the same square root of 2. Then we will get 1 multiplied by square root of 2 is square root of 2 only, and square root of 2 into square root of 2 will become 2, and p by q is as it is. Alright, so moving on. So this part is known as the rationalization part. However, now the things will be more easy and more attemptable as far as the solution is concerned. So it will be easily done, So moving on, people, that we have rationalized this number now, and now we are going to perform the proof on this number. So instead of directly proving this one, we have to rationalize it and we have to convert this whole number like this. Now we can operate on this number in order to prove that the number is irrational number. So let's see now. So we have this number, square root of 2 over 2 equivalent to p by q. So this is the same one, I have copied it down. Okay, so let's prove it now. So basic mathematical operation that we are going to perform, we are going to shift this 2 on the RHS side, which is p by q. So this is in divide, so it will go over there and it will be in the multiplication part. Now here, this is the rational one, and now rational multiply by rational, because we know that 2 is rational, 2 by 1 is rational particularly. So rational times rational will always end up with rational. So this is a well proven fact in mathematics, it's a basic property. So this whole system is rational only. Now here comes the contradiction, that in the LHS part, as we know that square root of 2 is irrational number, but the RHS part is showing the rational number. Then how this is going to be possible? Hence it is going to be impossible. Hence we have met with our contradiction, that the statement that we have taken in the assumption part is totally impossible to happen. Hence we have met our contradiction, and we can say that our assumption, now what was the assumption? The same, this was the assumption, that 1 by, let me highlight it highlighted for you people. So let us assume that 1 by square root of 2 is not an irrational number. Say it's a rational number. So we have assumed that 1 by square root of 2 is a rational number. But this is not possible. Hence we have met with the as we have met with the contradiction. Therefore our assumption is incorrect. In other sense, it is false to say, or it is impossible to say that this is going to happen. Hence 1 by square root of 2 is indeed an irrational number. So irrational number. All right, in fact it is irrational number. So we have seen I guess quite a few of the examples now, and I think and I hope that rest of the stuffs are quite clear to you people, that how the method of contradiction works and how we can prove, you know, a few of the as in the part of the illustrative example we have seen how to prove few of the numbers to be the irrational. So I hope this will be more you know, connectable and understandable for you people to know the irrationality proof. Okay.